Welcome everyone to yet another Third Thursday Telecon with the Stardust at Home team. And once again, we have Stardust at Home PI, Dr. Andrew Westphal, and our fellow duster, longtime duster volunteer, Mike, joining us online as well. And what are our topics today, Andrew?
Well, so I'll talk a little bit about where we are in terms of Stardust at Home and particularly foils at home, and then talk about another couple of topics that have come up that are really astrophysics related, but not directly related to Stardust. So, yeah. So shall I go?
Yeah, and I don't know if you also want to, we had this interstellar visitor as well that's been getting a lot of press lately. I don't know if you could say a couple of words about that as well at the end, that would be fantastic.
Well, I'll tell you what little I know. I don't actually have any inside information, but
well, I heard they found organic, so they think it's encased.
Oh, well then you know more than I do. Okay.
Okay. It might have a carbon outer layer. That's all I know.
Okay.
You can adjust that next time. You can brush up and then.
Yeah. Okay, we'll do that. Although, well, I will say something about that, just my personal take about it. So, okay, all right. Well, why don't I go ahead and give a bit of an update? Things have been we've been distracted really by other projects over the last month or so, and haven't made a lot of progress on the Foils at Home or Stardust at Home project directly. We have been talking about how to make software changes so that we can implement what we talked about last time, which is this idea of dividing up the data into smaller chunks, and then having teams who are going to be taking on individual blocks of data, so that we can make better progress. The problem is, just to recap, summarize where we are, we have a huge number of images, and we have fewer dusters than we used to have. And so the problem is we need to get over a threshold of number of eyes on each image before we can make a decision. And the number of images divided by the number of active dusters is large, and so it's going to take us a long time to get through all the data like that. So what we would like to do instead is to segment the data into smaller pieces, and then concentrate on those, and then be able to make definitive progress on those particular blocks of data. And we've talked a bit about having teams that will do that. So we have a list of changes that we need to make to the software. Robert has been working on that in collaboration with Will. And we think we now know what needs to happen, and now it's just a matter of getting the bandwidth with Robert and Will to make those changes, and that should happen shortly after the new year. But we haven't implemented those changes yet, but we know what to do. But let me talk about the things we have been working on also this last month, and we have some I think interesting news. So let's see. One of the things I think I mentioned was that last time we had just done a STXM run at the Advanced Light Source. So this is using this beamline that allows us to evaluate interstellar dust candidates in the aerogel pico keystones. We looked at two of them. We talked about this last time. We found that neither one of them are consistent with particles from the interstellar dust stream. That's disappointing in one sense. On the other hand, it's good. It's by itself is kind of a tour de force that we can actually make the measurement while the particles are still in the aerogel, and so we know that they are not interstellar. And that's something we didn't know before. So we're going to be looking at more. We've been allocated beam time for the upcoming cycle in the spring. So we actually have a substantial amount of STXM beam time, and we're going to be getting at least 3 more pico keystones from JSC, to look at, and hopefully more than that. So so we're hopeful that one of them at least is going to be interstellar, or at least an interstellar candidate. And there's one in particular that has a trajectory which is really pointing right back into the interstellar dust stream. It's track number, as I remember, it's track number 44, and it was one that
freeze up.
Yeah.
Okay, sorry about that technical difficulty we had. My laptop just seems to have died. So there was one track that we did not look at during the interstellar preliminary examination, and the reason is because the aerogel was too dense, and so we couldn't see through it. But now we have this nifty new technique to be able to thin pico keystones, working with Christy Gilly Rehak, and so we're going to, I think, be able to thin this keystone, and then we will be able to look at it. So this is one that looks very much like tracks 30 and 34. That is Orion and Heilbrook. So we're pretty excited about those. It's going to be a challenge doing the sample preparation, but that's okay.
And this is track 44, you said?
I think it's 44, as I remember. Yeah, that's right. Yeah. So we're looking forward to looking at that in the spring. So some other things that have been going on. We've been in that same STXM run. We were able to get some data that we've been looking for from these. This is soft ray X-ray absorption spectra from several particles from interplanetary dust. So this is a particular class of interplanetary dust particles are captured in the stratosphere, and they come from comets, almost certainly. They're called chondritic porous IDPs. They're sort of little fluffy bundles of tiny, tiny rocks. And they contain abundant particles called gems that are highly controversial in our field. Their origin is unknown, and what they look like is particles that are between 100 and 500 nanometers in diameter. They're quite a restricted size range. That is, you never see anything larger than about 500 nanometers, and you never see anything smaller than about 100. So they're not in a sort of a continuum of sizes. They're in this restricted size range. They have they're made of silicate glass. Well, shouldn't say glass. Silicate that is amorphous. We don't know whether it's a glass or not, but it is amorphous and contains metal and sulfide inclusions. And
now, wait, isn't aerogel silicate amorphous?
It is, yes, right, and it's not a glass. So there's an example of a glass or an amorphous silicate that's not a glass. But you can also produce amorphous silicates from irradiation by bombardment with heavy ions, and you can also make amorphous silicates by condensation. That is from a cooling, very, very hot gas. So glass is only one kind of amorphous silicate. So what the project we're working on is to try to measure or determine the state of iron in the interstellar medium, and we're using X-ray observations from the Chandra X-ray Observatory, which has been orbiting. Well, it's been making observations. It's outside the Earth's atmosphere, making observations of X-ray sources on the sky for a number of years, and we're using spectra, absorption spectra of iron that we see coming from X-ray binaries, and you can see the iron absorption, the absorption lines due to iron in the interstellar medium, and we're fitting those to spectra that we measure at the advanced light source. And so we got some measurements of gems, and we're now processing the data and scratching our heads a little bit about how to interpret what we're seeing. So it's too early to say exactly, but what it does look like is that the material in the interstellar medium is mostly chemically reduced. That is, it looks like mostly iron and sulfides, and very little of the iron is in silicates. And that tells us, in turn, should tell us about the formation, the chemical formation conditions in the early solar system, because what we see is that materials in the solar system were now oxidized And so it implies that there was that the early solar system in the nebula was chemically oxidizing, and that is if that's true, that's going to be quite important to our understanding of the early solar system's history. So that's one project that has been occupying our time. We're trying to get a paper out on this as soon as we can. We also have a piece of news which was unfortunately a little sad, but we think we understand it. So NASA every few years solicits proposals for a program called New Frontiers. And so New Frontiers is a line of NASA missions, planetary science missions, that run approximately $1 billion in cost in round numbers. So ones that are familiar are New Frontiers. I think it was New Frontiers. The first New Frontiers mission was the New Horizons mission to Pluto and the Pluto system. So obviously that was quite a spectacular success. New Frontiers 3 is the OSIRIS-REx mission, which just launched last year and is on its way to an asteroid called Bennu. And so the announcements were just made yesterday about the selections for New Frontiers 4. And I was part of a collaboration which was proposing to send a mission to a comet, to not land on a comet, but to collect material from the surface of a comet, and also to collect dust from the coma of a comet and return it to Earth. So somewhat like Stardust, but in a mode in which the spacecraft actually matches velocities with the comet. And so the collection is quite gentle, in contrast with Stardust, which flew through the coma of Cometville 2 at 6 kilometers a second. And so that's why we used aerogel and foils to collect that material. So there were 3 proposals. I believe that there were a total of 12 proposals for New Frontiers. There were 3 of them that were comet sample return missions, one from Goddard Space Flight Center, one from JPL, and one from APL. And we were collaborators on the proposal from APL called Corsair. This was something we put about 5 years of effort into. And APL spent a huge amount of resources in just developing the proposal. It's astonishing. I shouldn't share how much money was spent, but it's a large amount just to write the proposal. And so the announcements were made yesterday. What happens is that NASA selects somewhere between 2 and 4 missions to go into something called Phase A, in which the missions are given money to further develop their mission concepts and to try to retire some of their main risks. And then NASA, out of those missions that go through Phase A, NASA selects 1. So this is highly competitive. So we found out yesterday that we were not one of the missions to be selected for Phase A, and in fact, NASA only selected 2. One of them, I applaud. I think is a really interesting mission. Very, very, very cool. What it basically is a helicopter which is going to go to Titan. Yeah, it's called Dragonfly. And the idea is that it will go to Titan and it'll be kind of conceptually a little bit like the Mars rovers. It'll be able to move around and make measurements and observations and take pictures and so on. But instead of moving across the surface, in a wheeled way, it'll take advantage of the fact that the atmospheric pressure on Titan is about 1.2 bars. It's thicker than Earth's atmosphere. And so it's going to fly from one point to another. So it's just such a fun idea. It's just irresistible. So I totally understand why NASA selected it, and I think I would have done the same if I were on the selection panel.
Is that an astrobiology slanted mission in that, Titan has these methane rivers, I believe?
I don't know enough about it to really comment. I mean, I guess what I would say is that it's probably like the Mars rovers in the sense that it will be focused really on imaging and doing, chemistry. I'm speculating. I actually know very little about it. I don't even know how much is public. Sometimes, these things are not released. They're still proprietary, especially during the competition phase. So I don't know what its capabilities are. But my guess is it's probably not focused on biology except by accident. I mean, that's kind of the way the Mars rovers are, that, none of the instruments, or hardly any of the instruments, were really designed for detecting life directly. Viking did have some instruments like that, which were ambiguous, but, they are focused on life in the most immediate sense, that if you see, it's got a camera. So if you see something live or you see a fossil or something, well, then there you go, right? So could be something like that. I mean, if there is life on Titan, it is so alien that I don't even know, and I'm not an astrobiologist, but I couldn't imagine how you could even begin to design an instrument that would detect it if you were looking for, something microbial or something like that. The chemistry would be so wildly different than our own, life. So anyway, I think it's a great mission. I think it's cool. And our mission, so that mission is being run by APL, and we're speculating in our collaboration that the reason we didn't get selected, because we really think we had a very competitive proposal. Hard to believe that we would have been turned down for scientific or technical reasons. We think what may be going on is that NASA will not give the same institution to Phase A missions, partly just for practical reasons. It's probably impossible for APL or any large institution like that, even as big as they are, to support two simultaneous Phase A studies. And so that may be the reason. It's just as simple as that. Once they knew that they were selecting Dragonfly, that meant that they weren't going to select Corsair, which is our mission. But it is great that they did select a Comet surface sample return mission, and this is led by the way, Steve Squires, who is the guy who was the PI for the Mars rovers. So anyway, so it's disappointing news from a personal point of view, but I think the selections do make sense. And if I were, one of the big giant heads at NASA headquarters, I might have done exactly the same. It is a little bit of a surprise, though, that they only selected 2 missions for Phase A instead of 4. But anyway.
Can you say a little bit about Dr. Squires' mission?
All that I know about it is that it is going to be returning. I think the requirement from the NRC decadal recommendations is that the sample return be at least 500 grams of material from the surface. They're also intending to return volatile materials in a separate container. And I also heard a rumor that they're using the Hayabusa sample return capsule design.
Okay,
so that's as I know.
It is to a comet.
So it's actually going to 67P. It's going to Churyumov-Gerasimenko, which is where Rosetta went.
Okay.
So the advantage of that, I think, there are advantages and disadvantages when you think about where you're going to go. There's an advantage to going to a different comet because you're going to get something totally new. You're going to get information, from a completely different and new comet. The advantage of going to a place like going to a comet you've already been to and is well studied is that the terrain, the challenges, and so you can reduce risk by saying, okay, we already know a lot about this comet, and so we can even we even know so much that we can probably select right now, the sampling sites. Whereas if you go to a different comet, you have to spend a bunch of time doing reconnaissance to know where you're going to sample.
Right. Is the European Space Agency involved in this one?
I do not know. I doubt it. But, well, I shouldn't say that. Corsair had ESA involvement, so it could easily be. I just don't know one way or the other.
Okay.
I'm suspecting that there's JAXA involvement because of the Hayabusa capsule.
Right.
Yeah.
Well, it'd be great to get someone from that team to talk about the mission at some point on one of these telecons.
Yeah, that's a good idea. Mm-hmm. Right. Yeah. But again, they probably are not going to tell you everything because it's still proprietary and competition sensitive and all that stuff.
Right. Yeah.
So, so there are a couple of other things we're working on. One is I've been working on some Genesis analyses, and we're getting ready to do some measurements of new measurements. We're going to measure using this really fun shutter system that we just built. We're going to measure the abundance of manganese in the sun. Maybe I'll talk about that next time. Maybe by the time of the next telecon, we'll actually have a measurement. That would be cool. So the work we've been doing shows we really should be able to do this quite straightforwardly. You were asking about the interstellar asteroid. So I think you know more about it than I do, and I'll have to hear more about this organic stuff. I mean, this is a really surprising object, partly because as far as I know, there's nothing. I've never heard of anything in the solar system that resembles it, in the sense of its, we infer from its light curve that it is that it has a very large aspect ratio, shaped like a cigar, or something. And we've never seen anything like that in the solar system. It's hard to imagine, how that happens naturally. On the other hand, it's, so naturally raises the question: is it not natural? Well, that of course is the longest of long shots. That it's something artificial, and would be hard to understand it if it were. But it sure is fun, and it sure is intriguing. And in the paper a couple of days ago, they were talking about these supposed UFO sightings and stuff, and the Department of Defense is funding some, or I guess it was Congress really funded some studies of sightings of UFOs. I find this very far-fetched, and so I find this interstellar asteroid far more intriguing. It's this is a real thing, and who knows? And it is a brilliant idea to try to detect radio signals coming from it. I mean, it's also super long shot, but this is the first object we've ever seen like this. The first object, that's a macroscopic object from outside the solar system that we've ever seen, and so it's very intriguing. And it's also interesting that it is not it did not have essentially any volatile content. Was not a comet. And if you were going to guess what's the most common kind of interstellar object, you'd think it would be an icy body ejected from a forming solar system, in which case it really should be very comet-like when it comes into the inner solar system. And this is not like that. So curiouser and curiouser, who ordered that? It's really fun. So,
yeah, and I was just reading that some people think it has an organic coating on the outside, but I'm looking at an article right now. It's hard to tell what's known and what's just being theorized, hypothesized. But yeah, I mean, I think more will come out about that soon. This is a brand new story that just came out yesterday.
Okay. I see. I did not see that. I mean, I'm wondering if that's just an inference from its color. It's very red, and that is consistent with organics which have been exposed to interstellar to a radiation environment, for a long time, kind of like what you see on Pluto, and so that I'm guessing that that's where that comes from, but I haven't seen the article. Where did the article come out?
Well, the one I'm looking at right now is in Science Trends.
Okay.
I'll put the which who knows, the validity of that, but I'll put it in the chat here so that people can look.
Yeah. So that's all the news that's fit to print at the moment.
All right, Mike, any questions?
It's all very interesting. So is Dragonfly and the Comet sampling mission, those are both going to go forward then in this New Frontiers 4, or that still requires more evaluation?
Right. So they're both going into Phase A.
Okay.
And the Phase A is, I don't know what it will be for small class explorer missions. The Phase A usually lasts 6 months or so, and then they write a what's called a concept study report, which is I've got one on my shelf here. I'll actually show you what one looks like if I can. Let's see. So I want to make sure. So there's our concept study report. It's several, it's 3 volumes. I don't know if you can see that. That's from a small class explorer mission we had several years ago. So it's a big effort, but NASA funds that. Usually not enough to cover the costs, so the institution has to pony up some to cover all the costs of doing the study, and so they'll write a concept study report, each of them, after they've done their work, and then there'll be a shootout at NASA headquarters, and the teams will make their pitches, and there'll be reviews of the concept study reports, and then the associated administrator, Jim Green, will make the final decision about who gets selected, and only one will go forward.
Okay.
So, it's very interesting, I would say, politically and sociologically, how this is run. Ed Weiler used to be the associate administrator, and he made the point that in contrast with the human space flight, the human part, human space flight, or human, what's it called? Now I can't remember the acronym right now, but anyway, the human space flight part of NASA, the science directorate of NASA has always been highly competitive. So every time there's a big proposal announcement, or announcement of opportunity, depends on the line, but many institutions apply. For the small class explorer missions, which are sort of currently at around $150 million, I think, usually there are something like 50 proposals, out of which only one is selected. And writing a proposal is a big deal. It takes a lot of effort. So the fact that is competitive makes it, Congress really likes the fact that these are highly competitive. And so only the very best missions get selected to go forward. And so that's, for a long time, that has been a very, it's, if you're in the business, it's frustrating because your chances of getting any particular proposal are very low. But from the point of view of doing science and getting support from Congress to do science, it's a really good strategy.
All right, I'm getting a notice here from Zoom that we've got 4 minutes left.
Okay, so I went longer than I didn't think we were going to get 40 minutes. But
well, we also started. I think it records everything from the time we start and such. Yeah, right. So, any last minute questions, Mike?
No, I don't believe so. Look forward to the next update.
Okay. Well, thank you, and have a fabulous holiday, and I hope Myrna gets well soon.
Thank you. Appreciate that.
Yeah, give her our best, and we'll see you in the new year, and happy holidays there to you.
Hopefully you'll have all your fires out by then.
Yes, yeah, hope so. Boy, no kidding.
Rain.
All right.
Take care.
Bye-bye.
Bye.
Bye-bye.